Okay, today we're in the second day of Lesson 6.5, and we're going to talk about application problems with vectors. In example 7, a DC-10 jet is flying on a bearing of 65 degrees. So it's important to know what a bearing is, and you might want to take note about the fact that a bearing is measured clockwise from the north. A bearing is measured clockwise from the north. So when we have a bearing of 65 degrees, we're starting at the north axis, and clockwise would be to the right or down this way. So we're going 65 degrees this way, and that's our vector. And the airplane or the jet is going 500 miles an hour. So if we assume that the jet has flown for an hour, then we know the magnitude of that vector is going to be 500. And this would be the north line. This would be the east line. So our direction angle, that's different. The direction angle is the angle from the x-axis in a counterclockwise manner, and our direction angle would be 90 minus 65, or 25 degrees. So the direction angle for the flight of the jet is 25 degrees. That would be this angle. Now you can see that we have a right triangle here, with this being our theta angle or direction angle. And we need to find the form of the velocity of the airplane. So in vector form, we've got the magnitude times the cosine of the angle in the I direction, plus the magnitude times the sine of the direction angle in the j direction. So putting all of that together, we have 500 for the magnitude, cosine 25 degrees in the I direction, and 500 sine of 25 degrees in the j direction. So using our calculator, we can get some decimal approximations. 500 times cosine of 25 degrees is about 453 1500ths. And then the same thing with the 500 for the magnitude times sine of 25 degrees for the vertical movement, which is 211.31. So explaining that, what we know now is that the airplane travels, or the jet travels, about 453 miles in an hour, so miles per hour, on the east path, and it's going to travel about 211 miles, or in an hour, 211 miles per hour in the northward path. And all the while it's traveling 500 miles per hour on a 65 degree bearing. So that kind of puts into perspective what's happening. What does this component form mean for that vector? What does this mean in the trig form? This one's a little more abstract. Let's say we want to find the magnitude and direction of the sum of two vectors u and v. And those two vectors have magnitudes 6.9 and 13 respectively. So we'll call this vector u and this vector v, and the sum is the resultant. That's this vector here on the diagonal. We also know the angle between them measures 48 degrees. So this angle is 48 degrees. And this angle over here would be 48 degrees. Now, if a parallelogram has 360 degrees and two of the angles are 48, then that leaves us 264 degrees for the other two angles. So each of the other two angles would be 132 degrees. So we know this angle here is 132 degrees. And this angle is 132 degrees. And then we want to find the magnitude. So we want to know what the length of W is. And we want to know the direction angle of the two vectors. So this would be the direction angle of that resultant. Okay, so the first thing we did is we knew that the parallelogram, so the parallelogram angles sum to 360. And we had two that were 48 degrees, and we had two that were 132 degrees. So we put the puzzle together. And then next we know, if we use the side angle side rule from the law of cosines, we can find the length of that vector, the resultant W. So W is going to be the square root of 6.9 squared plus 13 squared minus 2 times 6.9 times 13 times the cosine of 132 degrees. And you can see right here that this is a side angle side with that, because the opposite sides are the same length. So with our calculator, I'm going to give that a go. So we got 6.9 squared and 13 squared minus 2 times 6 9/10 times 13 times cosine of 132 degrees. Cosine of 132 degrees. So about 18.348. So W is about 18.348, and they want us to round to the nearest whole number. So W is roughly 18, and they haven't given us any units, so that's all we know is it's 18 units. Okay, that's called the resultant. And then the last thing, we want to find the direction angle. So the direction angle, we could use law of sines, and that's going to be theta. So let's take a look at that. And we could say, since we know that this is 132, and we know now that this is 18.348, we could say side is to side as angle is to angle. And then we could convert that. So looking at that picture, we could say the sine of 132, so that's the angle across from the resultant, and the resultant was 18.348. That's proportional to our direction angle divided by the side opposite that. So in our calculator, to figure out what the radian measure is for our angle, we're going to multiply 6.9 times the sine of 132 and divide that by 18.348. So you ready to do that? Here we go. So the angle is, I forgot my notation for sine inverse, is 6.9, 6 9/10 times the sine of 132 degrees divided by 18.348. 0.348. So we don't want to round until we get to the end. So that's about 2.2834 radian answer. So let me clean this up here. This was supposed to say sine inverse. Sine inverse gives me my theta, and our theta is about 0.283241. We're going to multiply by 180 and divide by pi. So that answer times 180 divided by pi will convert to a decimal degree, so 16.23. And I believe our directions said that we needed to round to the nearest whole number, or the nearest degree. So our degree is about 16 degrees, and our resultant was about 18 units long to give the answer in the proper form. So that one's not too hard. Now, number 9 here, we want to look at a delivery truck driver requires a magnitude of force of 250 pounds to push a refrigerator freezer up a ramp at a 20-degree angle. So how much does the refrigerator weigh? So you can see we have two situations going on here. There's this force here. Force 1 is the weight of the refrigerator. And then force 2, see how it's parallel with the ramp? Force 2 is the force that we need, 250 pounds, to push against that freezer to keep it from sliding down the ramp. So if we resolve this right triangle here, we call this our theta, right? This is our angle. We could do sine of 20 is opposite to hypotenuse, and then we can solve for the weight. So that looks like sine of 20 degrees is the opposite. So the opposite is the force that the driver's using, and the hypotenuse is the weight of the refrigerator. So if we convert that to an equation, we can substitute F2 is 250 pounds divided by the weight of the refrigerator. So solving for the weight of the refrigerator is 250 pounds divided by the sine of 20 degrees. So that's pretty straightforward on our calculator. Let's see. So 250 pounds in the numerator divided by the sine of 20 degrees in the denominator. And that's a pretty heavy refrigerator, about 731 pounds. So the weight of the refrigerator, 730.951. We can put that in a sentence format and say the refrigerator weighs about 731 pounds. So that's a big refrigerator. Now, example 10, we're talking about bearings and navigation again. So remember, a bearing is measured clockwise from the north, and the direction angle is measured counterclockwise from the positive x-axis. And in this situation, we have a ship that sails on a bearing of 67 degrees east of south. So they're giving us a different type of measurement, saying east of south. So north, south, east, west looks like this. And if we're sailing our boat 67 degrees east of south, we're down here. So our bearing from the port is going like that. So if this is 67 degrees, then our directional angle is 90 minus 67. So our direction angle is 23 degrees. And we could say that the magnitude of the ship is going to be its speed, which is 15 knots. Oh, I got stuck there. Which is 15 knots. So the magnitude is 15. That's the hypotenuse. And here's our right triangle here. Okay? And we know our theta, our direction angle, is 23. So that means together we have an x component that is 15 cosine 23, and we have a y component that's 15 sine 23. So if you put that together as a vector, we can call that z. Then 15 cosine 23 in the I direction and 15 sine 23 in the j direction can be rewritten in linear combination using our calculator. So let's see, we got 15 and cosine of 23 degrees is 13.808 in the I direction, and 15 sine of 23 degrees in the j direction is going to be 5.861 in the j direction. And then if you need to write that in component form, we could write that as 13.808, comma 5.861. So all three of these are appropriate vectors, assuming no current, describing the velocity of the ship as a vector. And then our last example is the most difficult one. We've got to talk about what it means to be in static equilibrium. So we can say an object is in static equilibrium if the object is at rest and that the sum of all the forces acting on the object add up to 0. That means the resultant force is 0. So here in our situation for static equilibrium, we have this large construction generator. It weighs 1,500 pounds, and it's suspended by these two cables. We'll call one of them force 1. This one we'll call force 1. And this one over here we'll call force 2. And then the cable hanging down, that's going to be force 3. So the tension on each one of these cables, according to our definition, says when we add them together to be in equilibrium, they have to add up to 0. And we already know that force 3 is 1,500 pounds in the negative direction because it's going, if you imagine it as an x and y axis, it's on the y axis. And if we put a little dotted line here that's parallel to the beam, you see these two lines are parallel. You see that you've got two parallel lines cut by a transversal, and we have two parallel lines cut by this transversal. So alternate interior angles are equal, which means this angle is 40 and this angle is 25. And the three of them add up to 180. But to go from this axis over to here, that's going to be 155 degrees, since we need 180 minus 65 and then add the 115 to the 40. So if we're going to write a system of equations, that's what we said we could do. And we know that these three have to happen and that we know this amount. Then we need a name for force 1. And we could say force 1 is some weight, which I don't know. So we'll just say, I'm going to leave off the absolute value bars just so it's less confusing. So we'll say force 1 times cosine of 155 plus, let's see, we want to do it in the I direction, sine of 155 in the J direction, and we'll say force 2 is the magnitude times cosine of 40 in the I direction and the sine of 40 in the J direction, and then we have force 3. So this is magnitude, this is force 2, and this is force 1. So here we go. We got all the situations. Now we're going to write a system of equations. So the first thing, we had to figure out what was given, or what did we know. These are the things we know. And then we want to write a system of equations. Okay. So my system of equations, the first equation is going to be cosine. So if I think about this way, if we distribute that, we've got the cosine of 155 F1 and the cosine of 40, because I'm adding these two together, and they have to equal 0. And then we want to add up the sines. So the sine of 155 and the sine of 40. So the sine of 155 for F1, because I'm distributing that, and the sine of 40 with F2, and minus the 1500, that has to equal 0. So F1 and F2 and F3 have to be 0. And the only reason I don't have the 15 here is because we have F1 and F1, and this one would be 0, negative 1500. You follow that? I'm going to clean up my writing here. Hold on just a sec. Okay, so that looks a little neater than what I had. So if you think about this one, F3, and you can see what I was doing here. So I added up to make my system of equations. I added up all the column for cosine and then all the column for sine, and got that. Let's see, needs to be, oh no, that was right. Okay, so cosine of 155 and cosine of 40 add up to 0, and then this column, sine of 155 and sine of 40 and negative 1500, those three have to add up to 0. Now we're good to go. Hard to talk and write and keep it neat. So what I want to do is I want to call this one equation 1 and this one equation 2. And there we have our system of equations. And jump over to the calculator to make our life easier. We're going to turn those into decimals. So we've got cosine of 155 cosine of 155 degree. And that is negative, what was it, negative 906? So negative 0.906, and it's multiplied by F1. And then we got underneath it the sine of 155. Sine of 155 degrees. And that's, oh, I got too many. The sine of 155 decimal degrees. And that's 0.423 on F1. Then we got this column, cosine of 40. Degrees. And that's 0.766 for F2. And then we have the sine of 40 degrees. And that's decimal 643 for F2. And then what's happening? Minus 1500 equals 0. And then this one equals 0. So we have the same two equations again. This top one is still equation 1, and the bottom one is still equation 2. Now, what we want to do is we want to substitute for one equation. We're going to get a second page here so we can keep looking at them together side by side. So we want to substitute by this equation. Take equation 1. So from using equation number 1, we're going to get F2 all by itself. So negative 906 F1 minus 766 F2 equals 0. So we're going to solve for F2, which is going to make F2 is 0.906 F1 divided by 0.766. Okay, so we have a name for F2. I'm going to call that equation 3. And then if we use equation 2, which was 0.423 F1 plus decimal 643 F2, I see something else we can do. Let's take our calculator and figure out this number. So we're going to call that, let's see, decimal 906 divided by 0.766. Whoop. That's 1.183 times F1. So this is a good substitute right here. You with me so far? So 0.423 over here on F1 plus 643 times F2. But this is F2. See, F2 is this, 1.183 F1 minus 1500 equals 0. So if we add the 1500 and we add this, so let's do this arithmetic here. We got 0.643 times 1.183. So we're adding decimal 423 F1 plus decimal 761 F1, and we're putting the 1500 over there. So decimal 423 and 0.761 add up to 1.184 F1. That's 1500. And divide by 1.184. 1500 divided by 1.184 gives us a force of 1,266.89 pounds. And we go back up here, and we know F2 is 1.183 times F1, which we just found. So that answer times 1.183 tells me force 2 is about 1,498.73 pounds. Okay, so getting off of the view here, we can go back and answer our question. Force 1, what's the tensions on the cable? So force 1 or forces. Force 1 is about 1,267 pounds. And force 2, about 1,499 pounds. So that was a tricky one. That's the end of our lesson on vectors along with the applications. We got one more lesson in the chapter. See you next time.